Yeah, thanks, Andrea. Thanks to the organizer for invitation. This beautiful city. It's nice to see lots of familiar faces. I'm gonna be talking about gravity and amplitudes, and some application on how to go is essentially from amplitudes to observables. So the analog of QCD going to amplitudes to the cross section. So let me see. Yeah. So I think it's very important right now, given the current experiments and also the upcoming experiments with lots of data in different frequency bands for the binary mergers, that we try to study analytically the two-body problem, get new insights. And I want to say also, there is not only amplitudes, there are different approaches. So at least four. Post-Minkowskian is, of course, the one based on the amplitude expansion in the couplings, but it's also post-Newtonian. And these two are valid when the binaries are very separated. So it's kind of effective theory approach, what was proposed by Goldberger and Rothstein. But a low separation, like what is used right now for gravitational wave templates, is mostly like numerical relativity simulation. This is because we have only a few cycles in a spiral. They're or equal mass binaries, almost in circular orbits. But in the future, so right now we have LIGO in Virgo, Kagura, but in the future we're going to have some space-based detectors, and they're going to be sensing a different frequency band, where this binary spirals will have many more cycles, and in particular there will be extreme mass ratios, and for that, numerical simulations are very hard. So we really need the new tools to be prepared for the future, that not only numerical kind of simulation are not enough. So theoretical tools are really needed for this problem. So you see here, this plot in the mass ratio. So where the mass ratio is very large or small, depending on how you define it, sulfurs is a very interesting tool. It's kind of post-geodesic expansion. All these methods, as you see, have an overlap, okay, in different regions. So studying the interplay of this method is also very important. I'm not going to discuss much today, but I think this is a very, very important thing for the future. Why, I don't have to ask this question here, but one can ask why in perturbative QFT. So I think the new insights is that QFT tools provide a gauge invariant way of studying the point particle dynamics. They also offer a new perspective, or GR, like reproducing the black hole metric, for example, from a coupling of a massive point particle with a graviton. So these are very, very interesting, something completely new, different than the usual GR perspective. There are some advantages. So we get analytic compact expressions, many physical insights. It's scalable and flexible formalism. You can add various higher dimensional operators. And it has also great synergy with post-Newtonian gravitational surface, which I mentioned earlier. There are some disadvantages. I'll mention partially some of them. The one is the scatter to bound map. We need to go from hyperbolic orbits that are described by the S matrix to bound orbits. And also we need a resummation scheme. So the current perturbative expansion is very bad. Post-Minkowski expansion needs to be resummed. Otherwise, we cannot really go farther and apply this to the actual physical problem. Okay, so just show here a plot of the idea. So the idea is that we have our perturbative tools. It could be amplitudes, world length, or classical equation of motion. And we have three different expansions. So was it the one I mentioned, post-Newtonian? We have, of course, the post-Minkowskian, the amplitude base, and the gravitational surface. So something important that you see, like the post-Newtonian and the gravitational surface, they've mostly been applied to bound orbits until very recently. And so they could already be used for this binary spiral problem. Some problem we have to solve here, as I was mentioning, is this scattering to bound. So we need to really go from the S matrix observable scattering observables to the bound one. And first of all, we also have to compute the scattering observable from the amplitude, which is not trivial, especially for Kerr black hole spinning black hole, which is what I'm going to talk today. So mostly there are various tools like KMOC, which I'll mention, the Icona. We'll try to combine some of those. And then, of course, as I said, there is a pipeline. So to go to some resummation models that can be informed by numerical relativity as well. And then hopefully get some bound waveform modeling. So this is the reason why essentially we're interested in this particular problem. So we start with the KMOC formalism, Koster, maybe O'Connell. I think it's very it's very important. It's a very important formalism to clarify how to compute in observables for the two-body problem. So you take your wave packets, you scatter them some input parameter, and then you look at the outgoing state. So you have a very well preferred incoming state. You look at the symmetric evolution. You just go look at what comes out, and this is very clean setup, right? So you know what your energy of the system is at the beginning. For example, something for the bound case, you don't know when you do bound simulation. You don't know what your energy is. One of the biggest achievements, like in theoretical physics, like for the bound case, was actually finding out how from the first law binary dynamics the energy was coming out. So anyway, so the dynamics determined by an action. You can take your worldline model or some minimally coupled scalars models, and then you can perform it on perturbative expansion. The idea is you linearize the metric and you expand your coupling constant, and you get a bunch of diagrams. There are, of course, better on-shelf techniques to do that. Many of you are much more familiar than me as well on these kind of things. But ultimately, like, we want to really get to classical physics and get to classical observables. And some really nice observations was made by this author, like that. Basically, it's very natural to try to exponentiate the symmetric in the classical limit in terms of an N operator. Okay, this is like the Icona phase, the analog of WKB, essentially in quantum field theory, but with an operator here. It's also proposed by ACV in a different form, but I'm going to stick with this here and explain why later, because this is not exactly the Icona. The two differs. There is a change of basis, so the two things are different. So you study classical kinematics. Many of the authors, you can study like how the amplitudes behave in this for this classical scattering. Many of the authors of this heavy particle approach are here. I think it's a very natural way to try to parameterize essentially all the massless exchange to be soft. Just parameterize them with an H bar and take H bar to 0. It's something natural that we learn from quantum mechanics. Essentially, going from quantum mechanics to classical physics. So this is how we describe the classical limits. Something important that I was mentioning is this going to the exponents. Okay, it is this N operator, and so what it does for you is the following. So usually classical physics characterized by some sum or ladder, cross-ladder diagrams for relativistic, and having the exponent is this N operator. If you bracket it into two-body states, you get this object K, which will be the radial action in a conservative case, but it doesn't matter for now. But you see, you need only one diagram here and reproduce the full tower of exchanges in the quantum picture. So to make this manifest, you can just define like this kernel that I call in parameter space. This again is very similar to the Icona, but it will slightly differ in the basis at the end. So I'm just gonna say we use this bar variable for the Fourier transform in the transverse space, and you get this nice result. Pointing out this paper, also by Mao, Z, and others. And something that is nice about this is that, as we'll see, it will connect very well with classical physics and the Hamilton-Jacobi formalism as well. You can do the same for a radiative case. So you still look at the exponent. You state these matrix elements. Somehow these are, resumming. So from the previous, let me explain. From here, of course, your amplitude is always to the N operator. So you sandwich on the states on both sides. You always can find a relation. There is some subtractions essentially involved. So you can define some kernel. It's very important there are connecting and also disconnected contribution of this. It's very important to have disconnected contribution of this 5-point and possibly 6-point kernel and beyond. I'm not going to discuss much this 6-point. I'll show how they look in the observables. So what you can do is then with this formalism, try to, and that's what I've done with Sanshin, she was here, and Francesco Alessio recently. So trying to develop some coherent state expansion. This operator just taking essentially this N matrix elements and then go to B space. So you Fourier transform them, right? So you want is this generalization of this Fourier transform. Okay, so that's what makes this manifest in B space. Okay, so you Fourier transform in Q in the exchange momenta. So what you get is some expansion. This is very similar to the exponentiation, but I think it's on a different basis in this space. And there's still some conjectural part about exponentiation, but which hopefully we'll clarify in the future. So with this kind of idea, so see what's nice about this is that before there was an operator here. So the arithmetic was written as an operator. Now you have a scalar function. And this scalar will be your generating function of observables, just like this coherent state operator in terms of this 5-point and matrix element, 6-point and beyond. Let me also mention here I include 2 different 6 points because they're related to different channels, and they're related probably a crossing, but there is a kind of non-trivial thing to do. So anyway, doesn't matter for now. What you can do, use the K-MOC formalism, is computing in observables, okay? So take just your classical arithmetic in the form I mentioned, your operator, and then expand and use the BCH identity. And this allows to rewrite this as an iterated series of commutators, okay? So it's just an identity, just write in simpler form. And then what you can see is that if I'm able to turn commutators into some classical brackets, I can provide some method to directly evaluate these observables, and which I'm going to see is very efficient. So in general, you can have various types of observables, some in the two-body phase space, so some velocity, spin, and the hyperparameters, or some relative things in terms of ANA daggers, so the graviton modes, essentially. So you know what you want to do is really turn into the two-body dynamics on classical dynamics, just like the Hamiltonian, but on shell, completely gauge invariant on shell, but just like the Hamiltonian. Whereas like we use the graviton in the quantum form, you can also use the graviton as a field operator. So Jun Wook is going to tell us about that like in a couple of days. And this approach is very interesting. Like it's an alternative perspective on this Magnus expansion. But I'm going to proceed with what we've been doing here, like on the generating functionals for my talk. So here again, we take inspiration with different things. So we took inspiration a bit about the Icona, Tiziano operator, and now we take inspiration from the word line. So the word line is very important because it resums directly these superclassical terms that I mentioned. And here you can see also, if you take your trajectory, you have 3 trajectories, you can you can just conjecture a nice Poisson algebra between, it's something like X and P. So usually you're used to X and P with an Hamiltonian, but now X kind of goes to infinity, so it becomes the impact parameter. And so it becomes something on shell and gauge invariant. So what I'm going to say is a completely gauge invariant formalism for dealing with this. Of course, the spin-based Lorentz algebra, there's no surprise. And then what you can do is impose covariant SSE condition, which you know, is a summer condition on the spin, removing the boost degrees of freedom that Andres talked about, and then put it on shell, of course, with on shell kinematics, and then use transversality constraint. The transversality are just coming because I do the Fourier transform here. So you see this delta function. This is very important. The transversality constraints are very important. Is what it's the major condition that allows you essentially, you know, one of the 2 that allows you to turn these Poisson brackets in Dirac brackets. That's what we developed with Sanchin last year. And this generalized from the people in the EFT community, the Anson Regge brackets from non-shell scattering perspective. Yeah, so so there are novel kind of universal expression that you can get for the impulse, a spin kick in parameter shift. They get some conservative term. It's like the Hamiltonian again, but it's now gauge invariant, the KCL gauge invariant, the brackets as well. You have surroundation reaction terms. And there are some additional iteration terms. In particular, there are some related to this 6 point. So one of them is related to having 2 6 points on 2 sides of the cut, which is what we computed with Ruth, and also some work with Andrea and Matteo and Nathan, who are in the audience. And this is suppressed. It's a graviton loop. So graviton loops classically have to be suppressed. That's what we check in these papers. And of course, it doesn't rule out the possibility. I mean, it doesn't rule out the possibility that this connects with some 5 points. So it needs to be clarified what happens for the higher point kernels. We don't clarify in this work. It's something very important. But definitely, this graviton loops are suppressed. yeah, so using then this formula for the conservative case, you can get new results for the spin kick and test body impulse at 6 p.m., but the test body limits like S1, S2 to the 4. Some other results at 2 p.m. that we used recently for some work of Paolo, Lucille, and Enric and Lara recently. And then there's also some new results at 3 p.m. By Mao and Doan. And there are various related observables, include dissipation. Important thing is, can we find any structure? So this is what Mao talked about, so I will not mention much. But of course, you can, now that you have this Hamiltonian formalism, you know, that this kind of on-shell Hamiltonian formalism, you can say, okay, I set to 0, you know, the evolution operator is the operator, the Poisson bracket with the Hamiltonian. So I do the same with the radial action. And so I say, okay, quantity is conserved, this bracket is 0. It's very natural, completely gauge invariant condition. And then you can ask, okay, how do I characterize integrability? So I do the same as the Hamiltonian, but now from an on-shell perspective. I put a set of involution of charges in the reduced phase space, and if this commute, then you can find some nice, we conjecture you can find some nice integrable structure. There's some work that, as I said, doing Doan Graham is also in the audience, and Mao. And this we also use directly some conserved charges. We have some evidence of this symmetries that Mao talked about. So I'm going to skip because I don't have much time. So what happens for dissipation? So we compute now first radiation reaction term dissipation for the angular momentum. It's a very nice parameterization that was provided in this paper. And here you see it's all in the function of delta B, delta V, and delta S. So you can compute the K5, as I said, is a disconnected contribution. That's what computed the static angular momentum. It just comes from the soft factor. So you can compute that. And we found that the static piece depends only on delta V. This is very interesting because there was a lot of discussion on BMS and the dependence of why at 2 p.m. there is a radiating angular momentum, but not impulse on spin kick. Now you see it. So the impulse and spin kick are suppressed in this formula, and there's only delta B. So it's natural that there's a coordinate thing. It's just BMS frame dependence. And this kind of is very natural. It also connects with some BMS stuff that I don't have time to mention much. You can also do the waveform. Lots of experts here. It's also been done by Jung Wook, I may mention that. Here you find some correction, the 5 points, some commutator between the 4 point and 5 point. And this is an easier, I think, way to understand the cut term that gave a lot of troubles in the one loop waveform. So this exactly reproduced that cut term, and it reproduced a rotation that goes from B to BI conal, essentially. And of course, you get also 6 point connected with 5 point that needs to be studied at 2 loops. In particular, it's a very important calculation. Yeah, so this needs to be understood. Similar equation for fluxes, but yeah. We need to, once you have all of this, as I said, there are 2 problems. So even if you have scattering observables with this formalism, we need to go to bound and then do the summation. I'll just quickly sketch something that I think it's important to remind why we're doing this. So okay, this is just a state slide. I just add Dirac brackets or Poisson brackets. And I think it's a nice little tool. And as I said, it combines everything. So it comes from KMOC, iconal, and other ideas. So the scattering to bound, the idea is to do some analytic continuation in the energy. So go beyond the scattering to the bound case, doing incantation in the energy above threshold. There's been lots of results. The main takeaway is that there is some gauge invariant map. Either use the Hamiltonian, or there is a gauge invariant map between observables. It's just some analytic continuation in the energy. Or this also this nice rapidity variable P infinity, central mass momentum at infinity. Yeah, so it has to be proved the line spin extended to fluxes. And we recently looked at the waveforms and the geodesic order. The main takeaway is what this gives you, right? Which maps gives you between what I showed before and what we need for the bound case. So I want to explain this picture a bit more. So this is a scattering angle. It's some projection of the impulse I showed before, delta V. Okay. So you can add nice analytic continuation like by considering the 2 branches of this central mass and summing them together. It's an integrated observables, and you can get a Briasso advance. Recently, we'll also look at time delay and elapsed per time. They are infrared divergence because there is a 1/r potential, but the sum is finite. And if something finite is very important, so these things are important for causality and classical causality and other things. So it's related to the radial frequency and the redshift, for example. So the elapsed proper time is also a natural observable, this delta tau. In general, you can do the same for the fluxes, and we also look at the waveform. All this holds partially up to 3 p.m., 0SF, 3 p.m., until non-local in time effects come in. And this is a very important problem. People have been trying to work in the past few years, and that's to be still solved. Some preliminary progress for UV tail effects in LM space, but it's very important to push this program further to be able to say something about the bound case. But I think that this is very remarkable that there is a complete net of on-shell relation between on-shell observables, S metrics, and there is no gauge independent step in between. It's completely on-shell engaging variance. So we can use all our tools from Amplitudes to get to this point. I find that very, very interesting. Quantum case is not that easy. So you cannot do some kind of things like this in a quantum case. Something I want to mention recently. So there are some models for the resumation. So some of the every sum WB doesn't matter, like for the SOB PM rays here in the audience. And these are problems at high energies. We know the energy problem is a puzzle. So at 3 p.m., you get some proportional rapidity, factor of 3. And if you go a very large energy for the 4 p.m., you get gamma cube log gamma. And it's very important to understand the origin of these logarithmic divergences, the relation with massless limit. So something that we did recently, so it's long collaboration, Francesco, Alessio, Vittorio Del Duca, Emanuele Rossi, Ira Rothstein, and Michael Saavedra. We try to understand from there. So they have a recent nice paper on the SCAT perspective on the high energy problem. So talking about how the Glauber soft modes interact and how to essentially characterize the energy limit in classical gravity. And you find a very nice series of diagrams, multi-H diagrams, which give the leading contribution, the leading log contribution, like at high energies. Yeah, so the way to compute this is use arbitrary multi-region kinematics. So you can use some factorization. So just like you do in QCD, it's very nice. So here you don't have a Regge trajectory because they're quantum suppressed, but you can use jet function in convolution with soft function and study the evolution of the soft anomalous, the soft function here in rapidity space. Anyway, this is explained in this paper by Aaron and Michael. Something we found is that the emitted energy is freed of leading logs. So you see, this is the 3 p.m. In general, if you have a phase space, you would expect that you might get a logarithmic divergence. That's what happens when you take the cut of the H diagram in the way that the ACV did. But because there is a power suppression of the energy, these logs disappear. And somehow this means that the leading log cancel. And what we should actually study are subleading logs in the energy limit. And these are very important for the two-body kinematics. So Ira will talk more about this, so I don't have time. I conclude. I think there's promising application of particle physics to the binary dynamics, relatively new, past 8 years. I think it's crucial to study a phase space of classical dynamics, extract gauge invariant gauge generating functional. So from this object, remember, so apply the brackets, you get impulse, spin kick, input parameter shift, everything with a simple brackets once you know the generating functionals. So it's very powerful, I think. There's new symmetries, integrability, interpretation. There's also analytic continuation is actually based on the radial action, which agrees with these 4 points. So analytic properties of the radial action are much better than in other actions in particular, because this of course, there's a choice, like in choosing how they exponentiate, and this is very important for some analytic properties. It's crucial to understand no-local in time effects. Also, relation with other S functions, PN, GSF. I think there's lots to do here in the future. And I think also resummation perturbative nexus need to apply direct application, especially for eccentric bound binaries in the future. So yeah, thank you very much.